Hello everyone, this is Abdullah, and in this video, I will show you or present to you what IDDQ testing is. So IDDQ testing is based on, um, testing the stuck-at faults of an arbitrary circuit. So you have a combinational circuit or a sequential one, it doesn't matter. But in this case, you want to test the IDDQ because if there is any stuck-at faults at any nodes available in the circuit, and you want to know if there is a stuck-at fault or not, you want to test it, use IDDQ testing. And what's nice about IDDQ testing is you don't have to go through the circuit itself. All you need to do is just test the currents that are passing through the supply voltage and the ground. So what I'm doing here is I built a circuit, a combinational circuit. I didn't add any sequential elements. And I assume that you already have built your own standard cells, which are the OR gate and the NOR gate, as well as AND gates and OR gates and whatever, or maybe XORs and XNORs. And you built the circuit yourself, and you named every node correspondingly. I really recommend that you name the nodes in between as n and with an index. So n10, n20, n30 is what the intermediate nodes that I named here. I connected VDD to some of these inputs, and I have input voltage or input pulse voltage sources that I connected to the input of this combinational circuit. And at the output, you could just connect a capacitor with 10 femtofarads. So you don't have to have a really high capacitance here. It's only because I wanted a load capacitor, and that's about it. And you need to connect ground, a wire, and label it as ground. And that's about it. Moreover, you need to build the voltage sources. So for the inputs, I gave pulse voltage sources, voltage pulse sources, and what I did is I named these from A to D correspondingly because I want to connect different inputs, and then so inside these pulse sources, you could just give a 0 for voltage 1, 1 for voltage 2, and 5 nanoseconds starting from the A input, 5 nanoseconds, 1 nanosecond delay time, rise time, and full time could be something really small, insignificant, which is 10 picoseconds. The pulse width of this voltage source could be 2.5 nanoseconds. And what I did is I kept these constant. So full time, rise time, and delay time are constant, as well as these voltages. And as I go through the other voltage sources, which is B, C, D, what I did is I multiplied this by 2, and then I gave it to the other source. So for A, it's 5 nanoseconds. The pulse width is 2.5 nanoseconds. Click on OK, go to B. And what I did is with a period, I did 10 nanoseconds times 2. So times 2, the 5 nanoseconds is 10 nanoseconds. And I came to the pulse width and I changed it to 5 nanoseconds. That's about it. I do this for every other source. So this is 10 nanosecond. Come here. I did 20 nanoseconds, 10 nanoseconds, 40 nanoseconds, 20 nanoseconds. And my aim here is to have a 50% duty cycle. And I wanted to implement all the combinations at the input. So I want to cover every combination or every vector to this combinational circuit. So that's about it. I clicked on OK. What I did here is because I'm using the standard cell library of GPDK45, I use two sources. One that connects to VDD and the other connects to VSS, but you don't need to do that. All you need to do if you have your own standard cell library, which is you built your OR gates, your AND gates yourself, and the way you built it is just using, you don't need to implement this one, but all you need to have is this source. And so when you have the source, just give it a 1 volt DC voltage, and that's about it. And don't forget to name your VDD as VDD and not exclamation mark. Be aware of that. It depends on the circuit you have built, whether it has a VDD or a VDD exclamation mark. So global VDD or not, or local VDD. So be careful. And now that you're done with this, you have to name your intermediate nodes and every other node. And once you do that, open up an Explorer. So I already opened up mine. I assume that you have learned to open up an ADE Explorer. And once you open it, what you need to do is probe every node available in the circuit. So I probed A, B, C, and D. Remember, how did we do this? You go through output, and under output, you select to be plotted. It doesn't show up here right now because I'm using 2 monitors. But under output, you select to be plotted, and then it navigates you to the circuit. And in the circuit, you select the nodes available to be probed. And once you select it, it will show up here. Moreover, after you select the input nodes, so the primary inputs, you have the intermediate nodes, which are the N10, N20, and N30. So select those as well. What I'm talking about is these 3. So select those as well. And once you do that, it will show up here. Select the output is here. And select the positive and the negative terminals of the DC voltage source. So in my case, I selected this and this, but in your case, you will select the one here and here. All right. So once you do that, you're almost good to go. Remember to create an analysis. So the analysis is transient analysis. Do 42 nanoseconds if you are configuring your pulse voltage sources according to mine. Do 42 nanoseconds to cover every vector that we did. And once you do that, actually, you could do it 41. It doesn't matter. Except, please be sure to make it greater than 40 nanoseconds. And that's about it. Once you do that, just click on OK, and you have the transient analysis configured here. And now that you've done this, all you need to do is run the circuit. So before that, yeah. Now I want to tell you is the circuit is already configured so that it doesn't have any stuck at faults here. So run the analysis, and let's see how the IDDQ, or the current flowing through the supply voltages, are behaving. So let's do that. Let me close these. So I want to see how the circuit, or the current through the supply voltage, behaves. How are we probing the current? All you need to do is when you do outputs and then select to be plotted, it will navigate you to the schematic screen, right? So once it does that, click on the box rather than on the wire itself. So if you click on the wire, it will probe the voltage. If you click on the box, it will probe the current that is passing through that terminal. All right. So that's what I did. I clicked on those boxes just to probe the current that is passing through the sources. So once you do that, you will have these 2. And all I did is I named these 2. Oops. Move it here. Actually, move it here. Yeah. So once you do that, you have named, I named them as IDDQ, VDD, and IDDQ ground because you actually have two paths to where this current could flow. And one of them is the plus terminal and the minus terminal. So make sure to plot these two. And once you do that, you're good to go. And just click on run. So I obviously didn't save my schematic. I'm saving it now. So update and run. And it will start running the analysis. So we'll wait a couple of seconds now. And here we go. You have the output plotted, all the input combinations, as well as the intermediate nodes. So let's see what's happening here. So you can see the output is functional. So the circuit itself is functional. It's working perfectly fine. Yeah, this is the output. So you can see the output is behaving correctly. Well, you could go through all the combinations of the inputs and just make sure whether the circuit is functionally right or not by going through the truth table of the circuit itself. And once you do that and you made sure that your circuit is functionally correct, you could go through the analysis, the IDDQ analysis, and see whether there is a problem or not. So here, what IDDQ testing is based on, it's based on the measurement of current, right? So what I recommend is, since you cannot really understand anything here, I recommend that you create a new sub window. And in order to do that, you have to click on this logo or in this symbol. So click on it and it will create a sub window here. And why I did that is because I want to move these two current waveforms to this sub window. So now I can actually observe any fluctuations here and magnify the waveform itself because it's literally small here. You cannot understand any fluctuation, if there is any fluctuation or not. Maybe a little, but here it's much better to observe anything. So you can see here that we have maximums here, which is kind of normal because this is where the signals are transitioning at the same time. So if we were to look at the timing here, it's almost 1 nanosecond or 1.01 nanosecond. So that's where all signals are transitioning at the same time. So here is 1 nanosecond, right? So this is where all the signals are transitioning at the same time. It's quite normal to have a really surge in this current here. And this is, it's the same case for here because all the signals are transitioning from low to high as well. So you have really maximum currents here, or maybe I could even call it a short circuit current. But it's not really something that would really impact the circuit too much. It's instantaneous, and it's an impulse peaking here. So the current is really peaking here, here as well. Maybe here because you have maybe two signals transitioning rather than one signal. And here are static or steady state currents, and this is where all signals are steady and they're not transitioning. So they're static. And you can see here, on average, the current is around nanoamps, while here the peaking ones are close to 230 microamps, both of them. But there is no such thing as a significant impact to the circuit itself. So if we were to take the average of these currents, oh, and by the way, if we observe the other one, yeah, it's almost symmetrical to the negative terminal. But yeah, you could actually understand here, if you were to take the average of this, and you could, uh, there will be not much of a current flow or a current impact on the circuit itself. So let's keep this for records. And what I want to do is take a screenshot of this. So take a screenshot with window key and the shift key, and as well as the S. So window shift S, and you have a screenshot application open. So once you do that, take a screenshot of this, just in case we want to keep this for records. So yeah, we have a screenshot now. I want to keep it like this. Does it cover everything here? Just want to make sure. Yes, it does. It covers everything. So yeah, I'll minimize that for now. What I want to do is I want to implement a stuck at fault at an intermediate node. So let's do that. In order to do that, all you need is a resistor. So res under analog lib. Put that. And we need a VDC. So VDC under analog lib. Put that as well. And connect these two. And then change this resistor to 0 ohms, just to make it as a wire. All right. So once you do that, label these. So I want to connect this to N20. So for now, let's do N20 as a label. Connect it here and connect ground to here. All right. And by the way, if you want a stuck at fault of, so stuck at 1, you need to change the DC voltage to 1 volt. So that's about it. You have a stuck at 1 volt at N20. So let's just keep that here and save the circuit. And then go back to the analysis. Now we'll run this again and observe how the current behaves now. So this is how IDDQ testing is done. So we'll see whether there is any stuck at faults happening in the circuit itself. Let's wait a couple of seconds. See what happens. All right, got my plot. Here's the plot. And let's just expand this for now. So I expanded that. Right away, you could actually see this, realize that the output is not working correctly. It's not behaving as expected. We have 1 volt stuck at the output as well. And you can see that N30 is stuck at 1, N20 is stuck at 1. Initially, what we did is we connected we purposely added or intentionally added the stuck at 1 at N20. And it caused it caused the output to have a stuck at 1 as well. But here's the thing. In reality, you don't have access to the intermediate nodes. So in reality, you have faults almost everywhere in the circuit. Depends on the manufacturing process. So you could have a fault at N20 and your circuit stops working and it's literally not functionally correct. So in order to understand where this circuit has a stuck at fault, you do an IDDQ testing, and that's what we did now. And so let's create a sub window just to observe the both these signals. So control, click, click, then move these to the other subwindow. And realize here that you have a high current flow passing through the minus of the voltage source, of the supply voltage. So minus is where the ground is. So there is a high current or high steady state current passing through the ground terminal of this circuit. And it tells us that at this point of the transient analysis, which is between what, 1 nanoseconds and 11 nanoseconds, you have a high steady state current. And at the same time, between 11 and 21, or maybe, yeah, 11 till 31, you have a high steady state current, and your circuit is really consuming too much power. And this is really what tells us that where the stuck-at faults are. So in our case, what we did is the stuck-at 1 volt is at N20, right? And this happens when C and D, when does that happen? When does the IDDQ has a high current flow in the circuit? So if we observe the circuit again, and by the way, let's just compare it to the current behavior before. So remember, we had on average, it was close to 0. Now here, on average, it's really close to 100 microamps on 40 nanoseconds. So this is the behavior of IDDQ when there is a stuck-at fault in the circuit. So in order to understand the theory behind this, you need to go back to the circuit again. And what we did is we implemented a stuck-at 1 at N20, right? When does a high current flow happen here? When there is a stuck-at 1, let me ask you this question. What are the input combinations here when you have a high current or a high steady state current flowing through this node to the ground? So remember, the NOR gate has 2 MOSFETs connected in parallel to ground, right? Now, if we think about this, the truth table of a NOR gate, when does it have a 0 at the output? It only has a 0 at the output, or actually has 0 at the output, when at least one of these inputs are 1. So for an example, C is 1 and D is 0, right? Typically for an OR gate, the output would be 1, but this is a NOR gate, so the output is complemented and it will be 0. So when there's a 0 at the output and there's a stuck-at 1 at N20, you have a voltage difference or a potential difference between N20 at the and the output of this NOR gate, a potential difference of 1 volt. So when there is a potential difference of 1 volt, and the direction of this potential difference is from N20 to the output, so you would have a high steady state current flowing from N20 to the output of this NOR gate to the ground of this NOR gate. All right. So that's the reason why you have a high steady state current. Otherwise, when the circuit is functionally correct and behaves normally, there wouldn't be a steady state current. So there wouldn't be a potential difference between N20 and the output of this NOR gate. So that's about it, really. And you have the other case, which is a stuck-at 0, and you can implement that on N10 with a 0 ohm. and really observe what happens when there is a stuck at 0 here, and the output of this OR gate has a 1 volt. So you basically have a potential difference of 1 volt at the output of this and a 0 volt at the node N10. And you will have a steady state current as observed here as well. So yeah, that's about it for the steady state current or for the IDDQ testing. And yeah, you could really observe the steady state currents. It's usually higher than what's expected. And once you do this, so let me go through this again. You want to choose C and D and put it here. Highlight these. And you can see here, so when both C and D, so remember what C and D is. C and D are the inputs to this NOR gate, right? So remember, we said when both of these inputs are 1, you should have a steady state current that is high here. So yeah, that's what's observed. And if we go, even if we have one input that is low and the other input is high, so in this case D is high and C is low, you still have on average, 100 microamp steady state current flowing. The same case is for the other one, so at least one of them is logic high. And you have a steady state current here flowing. That is on average, again, 100 microamps. So yeah, this is what IDDQ testing is.